Let's begin with something that feels simple, but isn't. An electron is usually introduced as one of the basic building blocks of nature. You hear that atoms are made of electrons orbiting nuclei, and that electrons flow through wires to power your phone. That description works well enough for daily life, but it hides something deeply unsettling. Every electron we have ever measured, anywhere in the universe, behaves exactly the same way. Not almost the same, not close enough that we can't tell the difference. Exactly the same. Take an electron from your body and compare it to one coming from a distant star. Measure its mass. Measure its charge. Measure its spin. Every single value is identical down to the limits of our most precise experiments. Physics does not say electrons are similar objects produced by the same factory. Physics says they are fundamentally indistinguishable. This is already strange, even before things get quantum mechanical in a serious way. In everyday life, identity matters. This cup is not that cup. Even if two objects look identical, they have different histories. One was scratched yesterday, the other wasn't. One fell on the floor once, the other didn't. Objects carry their past with them. We are so used to this that we rarely notice how deeply it shapes our thinking. Electrons don't seem to work like that. When physicists write down the equations that describe electrons, there is no label for electron number 1 or electron number 2. If two electrons interact and then separate, the theory does not allow you to say which outgoing electron corresponds to which incoming one. The question itself has no meaning. It's not that we lack information. It's that nature does not appear to store that information at all. That's a hard idea to swallow because it clashes with how we naturally think about the world. We imagine particles as tiny balls, each one a separate thing, moving through space like microscopic planets. But electrons refuse to behave like that picture. They are not little objects with personal identities. They are more like identical ripples that can overlap, merge, and separate without ever becoming distinguishable individuals. This perfect sameness is not a philosophical preference. It is forced on us by experiment. If electrons had even the tiniest built-in differences, the equations of chemistry would fail. Atoms would behave unpredictably. Life, as we know it, would probably not exist. The universe is stable precisely because electrons are not individuals in the usual sense. Already, we are facing a quiet but profound problem. If electrons are not distinguishable objects, what does it even mean to say that there are many of them? What does many refer to if you cannot, even in principle, tag one and follow it through time? Most of the time, physicists avoid that question because the math works without answering it. But Richard Feynman had a habit of poking at questions everyone else politely ignored. And when he looked at this strange sameness of electrons, he wondered whether our usual picture of many identical particles might be hiding a much more radical possibility. If the first strange thing about electrons is that they are perfectly identical, the second is even more unsettling in quantum physics. The idea of identity itself starts to fall apart. In everyday life, identity feels obvious. You can point to an object and say it is the same one you saw yesterday. Even if it changes slightly, you believe it has remained the same thing through time. This way of thinking works because the world of chairs, stones, and people is built from objects that keep track of their own histories. Quantum particles do not seem to do that. When physicists describe electrons using quantum mechanics, they do not treat them as tiny labeled objects. Instead, electrons are described by a shared mathematical wave function. This wave function does not belong to one electron or another. It belongs to the entire system at once. If you have two electrons, the theory does not allow you to say, this part of the wave belongs to electron A, and that part belongs to electron B. The electrons are mixed together in a way that makes the very idea of individuality meaningless. This becomes clear when electrons interact. Imagine two electrons approaching each other, scattering, and then flying apart in different directions. In classical thinking, you would naturally ask which outgoing electron came from which incoming one. In quantum mechanics, that question has no answer. The mathematics does not just fail to tell you, it actively refuses to define it. The final state includes both possibilities at once, and there is no experiment that can ever separate them. This is not a limitation of our technology. It is a feature of the theory that has been tested again and again. Electrons behave as if they have no personal identity to preserve. Because of this, Quantum mechanics treats identical particles in a radically different way from classical objects. Swapping two electrons changes nothing at all. The physical situation is exactly the same before and after the swap. Nature does not notice the difference, because there is no difference to notice. This is why electrons follow special rules, such as the Pauli exclusion principle, which governs the structure of atoms and makes chemistry possible. From a human perspective, this is deeply uncomfortable. Our language is built around the idea of individual things. We talk about this electron and that electron as if they were separate entities with their own stories. But that way of speaking is a convenient shortcut, not a statement about how reality truly works at the smallest scales. What quantum physics suggests is that electrons are not objects in the ordinary sense at all. They are more like excitations of something deeper, patterns that appear and disappear without carrying identity across time. The idea of which one is which simply does not apply. This is the point where our everyday intuition starts to fail completely. We keep trying to force quantum behavior into classical boxes, and it keeps slipping out. Identity, which feels so fundamental in daily life, turns out to be optional in the quantum world. Once you accept that identity is not built into electrons, a door quietly opens. If electrons do not possess individuality, then the statement, "there are many electrons," becomes less straightforward than it sounds. And that is exactly the crack in our thinking that allowed Feynman to ask a question most physicists would never bother to ask. What if what we call many electrons is really something much simpler, seen through the distorting lens of time and measurement? To see where this line of thinking becomes truly strange, we need to look at antimatter, and in particular at the positron. Positron is often described as the antimatter version of the electron. It has the same mass, the same spin, but the opposite electric charge. When an electron and a positron meet, they annihilate and turn into pure energy. That much is familiar. What is not familiar is how positrons appear in the mathematics of quantum physics. When physicists write down the equations that describe electrons, something unexpected happens. Those equations naturally allow solutions that look like particles with negative energy moving forward in time. At first, this seems impossible. Negative energy makes no physical sense in an ordinary picture of the world. But instead of throwing these solutions away, physicists discovered that they could reinterpret them in a surprising way. A particle with negative energy moving forward in time behaves mathematically exactly like a particle with positive energy moving backward in time. When this reinterpretation is applied to the electron's equations, the result is a positron. In other words, the positron can be described as an electron traveling backward through time. This is not a poetic metaphor. It is a precise statement about how the equations worked. If you reverse the direction of time in the mathematical description of an electron, you obtain the correct description of a positron. Every prediction that comes out of this picture matches experiments perfectly. Now pause for a moment and let that sink in. Physics, at its most successful and precise level, allows a perfectly valid description in which a particle moves backward in time. Not as a speculation, not as science fiction, but as a mathematical equivalence built into the theory itself. Of course, this does not mean that we observe electrons zipping backward through time in everyday life. What it means is that our usual way of thinking about time as a simple forward, flowing river may not be fundamental. Time, like identity, may be something that emerges from deeper rules, rather than being built into the universe at the start. This strange time reversal property was one of the things that caught Feynman's attention. He noticed that if positrons can be treated as electrons moving backward in time, then the distinction between matter and antimatter becomes less absolute than it seems. The difference may depend on how we slice reality along the direction of time, rather than on there being two fundamentally different kinds of particles. Once again, this clashes with human intuition. We are creatures who remember the past, but not the future. For us, time has a clear direction, and the idea of moving backward through it feels absurd. But the equations of physics do not share our psychological preferences. They are mostly indifferent to the direction of time, and sometimes they even work better when time is allowed to run both ways. What makes this especially unsettling is that we cannot point to any experiment that tells us whether the backward in time picture is real or just a convenient mathematical trick. Both interpretations give the same results. Physics remains silent on which story, if any, is the true one. And this silence is important. It shows us that some of the categories we rely on, past and future, cause and effect, particle and antiparticle, may not be as fundamental as we think. They may be different ways of describing the same underlying process. When Feynman looked at this, he did not see a bizarre curiosity to be ignored. He saw a crack in our usual picture of reality. If electrons and positrons are just the same thing, seen along different directions of time, then the question of how many electrons exist in the universe becomes far stranger than it first appears. Now we can finally approach the idea that made this whole discussion famous, or infamous, depending on how you look at it. Once you accept that electrons have no individual identity, and once you accept that positrons can be described as electrons moving backward in time, a peculiar possibility presents itself almost on its own. Imagine that there is only one electron in the entire universe. Not one type of electron, but one actual entity. This single electron traces out an incredibly complicated path through space-time. Sometimes it moves forward in time, and sometimes it moves backward. Wherever it moves forward in time, we observe it as an electron. Wherever it moves backward in time, we observe it as a positron. From our limited perspective, trapped in a forward, moving slice of time, this one tangled path looks like many separate particles existing at once. We see countless electrons scattered throughout space, interacting with atoms, flowing through wires, and producing light. But in this picture, those are not many electrons at all. They are many appearances of the same electron at different points along its journey through time. A useful way to picture this is to forget about time for a moment and think in terms of geometry. Imagine a long, looping thread woven through a three-dimensional fabric. If you take a thin cross-section of that fabric, you might see many points where the thread passes through the slice. To someone who only sees the slice, it looks like many separate threads. But in reality, there is just one thread looping back and forth through the fabric. In this analogy, the fabric is space-time, the thread is the electron, and the slice is our present moment. Every time the thread crosses the slice moving in one direction, we call it an electron. Every time it crosses moving the other way, we call it a positron. This picture explains something that otherwise feels almost magical, why electrons are perfectly identical. If there is only one, then of course there is no difference between them. Their sameness is not a coincidence or a law imposed from the outside. It is a simple consequence of there being nothing else to compare them to. It also gives a strikingly simple way of thinking about antimatter. Instead of being a separate kind of substance, antimatter becomes matter viewed from the opposite direction in time. The universe does not need two kinds of particles, only one kind of behavior traced along a more complex path than we usually imagine. At the same time, this idea pushes directly against the limits of what we can comfortably visualize. Our brains are not designed to think in four-dimensional space-time, let alone to picture objects doubling back in time. We instinctively want to ask where the electron is really located, or which part of its path corresponds to this electron and not that one. But those questions assume a notion of identity that the theory itself has already discarded. It is important to be clear about what this idea is and what it is not. It is not a standard model of particle physics. It is not a theory used to calculate experimental results. It does not replace quantum field theory. Instead, it is a conceptual experiment, a way of compressing several strange facts into a single, unsettling picture. Feynman did not present this idea as a belief about how the universe literally works. He presented it as a reminder of how far removed the true structure of reality may be from the stories we tell ourselves. If one electron moving back and forth through time can reproduce everything we observed, then perhaps our way of counting particles is not as fundamental as we assume. At this point, it is completely reasonable to feel that something has gone wrong. The idea of a single electron weaving back and forth through time, appearing as countless particles spread across the universe, sounds less like physics and more like a trick of language. Our instinct is to reject it immediately, and that reaction is important because it reveals how strongly we rely on certain assumptions about how the world must work. One of those assumptions is that causes come before effects, that time moves in a single direction, and that objects exist as stable things at each moment along that direction. The one electron idea quietly violates all three. It suggests that what we call many things might be a single process seen in pieces, and that the order of those pieces depends on how we slice time rather than on how reality is fundamentally organized. The discomfort comes from the fact that our everyday reasoning is built for survival, not for truth at the deepest level. We learn to track objects because it helped us avoid danger and find food. A stone thrown yesterday is the same stone today. A predator that ran past you a moment ago may still be nearby. This way of thinking works extremely well at human scales, so we unconsciously assume it must work everywhere. Quantum physics keeps reminding us that it does not. When physicists first encountered quantum behavior, they tried very hard to preserve classical ideas like identity and continuity. They imagined particles as tiny dots following precise paths, even when the equations resisted that interpretation. Over time, it became clear that forcing reality into those categories only created confusion. The math worked best when particles were treated not as objects with histories, but as abstract entities whose individuality did not matter. The one electron picture exaggerates this lesson until it becomes impossible to ignore. It takes the already strange features of quantum theory and pushes them into a single, shocking image. That is why it feels absurd. It is not introducing new weirdness so much as concentrating existing weirdness into a form we can no longer comfortably ignore. What makes this especially interesting is that nothing in our observations directly rules the idea out. We do not observe individual electrons persisting through time in a way that would contradict it. We observe interactions, measurements, and patterns, all of which are compatible with many different underlying stories. The one electron story happens to be one of the most extreme. This forces us to confront an unsettling fact about science. Theories are not mirrors of reality. They are tools for organizing observations and making predictions. Very different pictures can sometimes produce the same observable results. When that happens, nature does not step in to tell us which picture is really true. So why take this idea seriously at all? Because it exposes the limits of explanation. It shows that even when our equations work perfectly, our intuition can still be completely lost. It reminds us that asking, what is really happening, may not always have a clear answer in the way we expect. The one electron idea matters not because it is likely to be literally correct, but because it strips away comforting assumptions. It challenges the belief that the universe must be built from many separate things moving neatly through time. It suggests that what we call absurd may simply be a sign that we are trying to understand a reality that was never designed to fit inside the concepts of everyday thought. And once that realization settles in, it becomes harder to laugh the idea away. The absurdity is no longer a flaw in the idea itself. It is a reflection of the gap between human intuition and the structure of the universe. If the one electron idea sounds outrageous, it is fair to ask what, if anything, it actually gets right. Stripped of its more dramatic imagery, the idea succeeds because it aligns surprisingly well with several deep and well-established facts about nature. These are not speculative claims or philosophical guesses. They are features of the universe that modern physics has measured with extraordinary precision. The most obvious success is the perfect sameness of electrons. In every experiment ever performed, electrons have shown exactly the same mass, charge, and spin. There is no known mechanism that would enforce this level of uniformity across billions of years and unimaginable distances. The one electron picture bypasses the problem entirely. If there is only one electron, then perfect identity is not something that needs to be explained. It is automatic. Another point in its favor is the relationship between electrons and positrons. In standard quantum theory, positrons appear naturally as time-reverse solutions of the electron equations. This is not an optional interpretation layered on top of the math. It is built directly into the structure of the theory. The one electron idea takes this mathematical symmetry seriously and asks what it would mean physically. By doing so, it unifies matter and antimatter into a single continuous process instead of treating them as fundamentally separate entities. The idea also fits comfortably with the way quantum physics handles identity. In quantum mechanics, particles of the same type are not tracked individually. Calculations depend only on how many particles are present, not on which is which. Swapping two electrons changes nothing measurable. This lack of individuality is not a flaw in the theory. It is essential to explaining atomic structure, chemical bonding, and the stability of matter. The one-electron picture simply pushes this principle to its logical extreme. There is also a deeper conceptual advantage. The idea encourages us to think of particles not as tiny objects, but as events or interactions spread across space-time. This aligns closely with modern quantum field theory, where particles are understood as excitations of underlying fields rather than as standalone entities. From that perspective, the electron is already less like a thing and more like a recurring pattern. The one-electron idea exaggerates this view, but it does so in a direction that physics has already been moving for decades. Importantly, none of these points require us to believe that the one-electron picture is literally true. Its value lies in how efficiently it organizes several strange but real facts into a single mental image. It acts like a stress test for our understanding. If an idea that extreme can still remain consistent with known physics, then our usual intuitions about particles and time must be far less reliable than we assumed. At the same time, the idea remains firmly grounded in known science. It does not introduce new forces, hidden dimensions, or untestable mechanisms. It relies entirely on well-established features of quantum theory and relativity. That is why it continues to be discussed, not as a serious proposal for rewriting physics, but as a powerful way of revealing how alien the quantum world already is. In that sense, the one-electron idea succeeds precisely because it does not ask us to accept new facts about the universe. It asks us to rethink what the existing facts might be telling us, if we are willing to follow them all the way to their most uncomfortable conclusions. For all of its elegance and unsettling simplicity, the one-electron idea runs into serious problems as soon as we ask it to do the job of a real physical theory. These problems are not minor technical details. They go to the heart of how modern physics actually works and why this idea remains a thought experiment rather than a description of reality. The most immediate difficulty is that the idea does not provide a clear, workable mechanism for how a single electron could account for the enormous number of electrons we observe at the same time. In everyday experiments, we detect vast numbers of electrons interacting simultaneously in different locations. While the space-time thread picture offers an intuitive visualization, it does not translate into precise calculations. Physics demands equations that can be used to predict measurable outcomes, not just images that feel satisfying. Modern particle physics relies on quantum field theory, a framework in which particles are treated as excitations of underlying fields that exist everywhere in space. In this view, electrons are not persistent entities moving through time, but momentary disturbances in an electron field. The one-electron idea does not fit naturally into this framework. It treats the electron as something more like a classical object with a continuous trajectory. Even if that trajectory is allowed to bend through time, that clashes with how particles are actually handled in the most successful theories we have. There is also the problem of interactions. Electrons interact with electromagnetic fields, with each other, and with other particles in highly specific ways. These interactions are described by well-tested rules that assume the presence of multiple electrons as independent participants in a process. The one-electron picture does not offer a clear account of how a single electron could interact with itself in ways that reproduce all these phenomena without leading to contradictions or double counting. Another serious limitation is the lack of new, testable predictions. In science, the value of a theory is not just that it explains what we already know, but that it risks being wrong by predicting something new. The one-electron idea does not do this. It reproduces known results only by being carefully interpreted to match existing theories. There is no experiment we can perform that would clearly distinguish a one-electron universe from a many-electron universe. Without that, the idea cannot be elevated beyond a conceptual exercise. There is also a deeper conceptual issue. Even if electrons lack individuality, counting still matters. The universe behaves differently depending on how many electrons are present in a region. Electric currents, chemical reactions, and atomic structures all depend on electron number in precise ways. The one-electron picture must somehow recover this effective multiplicity. But it does so only by appealing to appearances rather than to a clear underlying mechanism. Perhaps most importantly, the idea does not clarify the nature of time itself. It relies heavily on the notion of motion backward and forward through time, but it does not explain what time is, why it has the structure it does, or why our experience of it is so strongly one-directional. It uses time as a stage for the idea without explaining the stage itself. For these reasons, physicists do not regard the one-electron idea as a serious contender for describing reality. It is incomplete, non-predictive, and incompatible with the mathematical machinery that has proven so successful. But its failure is instructive. It shows us that even a beautifully strange idea, one that aligns with several deep truths, can still fall short of what science ultimately requires. The human struggle with concepts like the one-electron idea reveals more about our cognitive limits than about physics itself. Our minds evolved to navigate a world of medium-sized objects moving in 3 dimensions and flowing through time in one direction. This world is mostly predictable. It contains persistent objects, cause and effect chains, and identities that can be tracked over hours, days, and years. Every skill, intuition, and pattern recognition tool in our brains is tuned for that kind of environment. Quantum reality, however, is built from very different rules. Particles do not carry identifying labels. Their identities are meaningless outside of specific interactions. Cause and effect blur when events are connected probabilistically rather than deterministically. Time may not be a simple one-way river, and objects may not exist independently of measurement. These features of reality are not merely difficult to imagine, they are actively counterintuitive. When humans try to grasp them using classical thinking, confusion is inevitable. The struggle begins with language itself. Words like electron, particle, or even existence carry baggage from everyday life. When we say electron, we unconsciously think of a tiny ball with a location, a history, and a unique identity. In reality, an electron is a pattern of interactions in a quantum field. It does not have a personal narrative in the sense that we understand narratives. Our language misleads us into assuming that quantum objects behave like macroscopic objects, creating mental friction that makes theories like the one-electron picture feel absurd. Even trained physicists encounter this friction. Equations do not rely on intuition. They are precise and internally consistent, yet they often produce predictions that seem nonsensical when translated into words or mental images. One particle can interfere with itself, be in multiple places at once, and mathematically even move backward in time. Humans instinctively resist such ideas because they violate every survival-honed expectation about the world. Accepting them requires a shift from visualizing reality to thinking abstractly about processes and relationships, which is cognitively demanding. Another factor is the role of experience. Our knowledge of physics comes from experiments conducted at scales far removed from daily life. Electrons and positrons, atomic orbitals, quantum fields, these are phenomena that cannot be observed directly, only inferred from precise measurements. Without direct sensory experience, the mind struggles to anchor understanding. The one-electron idea pushes this even further by suggesting that all the particles we detect might be manifestations of a single entity following a complex path through time. This is not something the brain evolved to represent. It is an alien concept requiring suspension of deeply ingrained assumptions. This difficulty explains why humans tend to reject or trivialize ideas like the one electron theory instinctively. It is not a failure of intelligence. It is a natural consequence of evolution. Our brains are optimized for survival in the macroscopic world, not for intuitive mastery of four-dimensional space-time and quantum indistinguishability. Grappling with such ideas requires conscious effort, careful abstraction, and willingness to accept that some aspects of reality may never comfortably fit our mental models. Ironically, this struggle is precisely what makes these concepts so valuable. They highlight the limits of intuition, revealing that the universe operates according to principles that do not cater to human expectations. The one-electron idea exposes a tension between the reliability of mathematics and the unreliability of intuition. It reminds us that reality does not owe us comprehension, and that curiosity and humility are essential tools for navigating a world that is fundamentally stranger than our senses suggest. Human difficulty with quantum identity, time reversal, and particle indistinguishability is therefore not a flaw. It is evidence of how alien the universe is compared with everyday life. By confronting these limits, we expand not only our knowledge, but our capacity to think beyond the constraints of instinct and habit. The one-electron idea forces a confrontation with this boundary, highlighting both the power of physics and the limits of human cognition. The one-electron idea is more than just a curious footnote in physics. It is a lens through which we can examine the nature of scientific understanding itself. Science is often described as a quest to uncover objective truths about the world. But the one electron picture reminds us that even the most precise theories can leave room for multiple, radically different interpretations. Equations may predict outcomes with extraordinary accuracy, yet how we visualize what is actually happening can be profoundly misleading. This is one of the reasons humans struggle to accept concepts like quantum indistinguishability and time-reversed particles. In classical thinking, reality is a collection of individual objects, each with its own story. Each stone, each tree, each electron has an identity that persists over time. But quantum mechanics challenges this assumption at a fundamental level. The equations work perfectly well without assigning individuality to particles. Whether there is one electron moving through time in a convoluted path or many electrons behaving identically makes no measurable difference in the predictions we obtain. What matters is the pattern of interactions, not the individual identities of the actors. This disconnect between human intuition and the formalism of physics is a source of both frustration and fascination. We have evolved to think in terms of objects, causes, and sequences because it helped our ancestors survive. Tracking a predator or remembering the location of a water source requires these mental tools. They are deeply ingrained and operate automatically. Quantum phenomena do not conform to these rules, so when we attempt to conceptualize them in familiar terms, contradictions and absurdities appear. This is why the one electron idea feels so alien. It lays bare the incompatibility between our cognitive framework and the structure of the universe. Yet this tension is precisely what makes the concept enlightening. By taking the logical consequences of quantum mechanics seriously, the one electron idea forces us to confront the limitations of conventional reasoning. It shows that reality may not be composed of separate, identifiable units, but instead of processes and relationships that only appear to be multiple objects when observed from our limited temporal perspective. Time, identity, and even the distinction between matter and antimatter may emerge from a deeper structure that is largely hidden from our direct experience. This realization has profound implications for how we think about knowledge itself. Scientific theories are not mere catalogs of observable phenomena. They are frameworks for organizing and predicting patterns. Multiple frameworks can produce identical predictions while suggesting vastly different pictures of reality. The one electron picture is an extreme example. It reproduces the known behaviors of electrons while radically altering our mental model of what those electrons actually are. It demonstrates that understanding in physics is often more about consistency and predictive power than about matching human intuition. Accepting this can be unsettling, but it also expands our intellectual horizons. It encourages a mindset in which questions about what is really happening are approached with caution. Sometimes the most honest scientific answer is not a definitive story, but an acknowledgement of ambiguities. The one electron idea exemplifies this by presenting a logically consistent, mathematically compatible scenario that defies everyday reasoning. Its value lies not in being true or false, but in revealing how deeply alien the quantum world is and how limited our instinctive understanding can be. Ultimately, the one electron idea teaches a form of intellectual humility. It reminds us that reality is not obligated to make sense to human cognition. Even the most precise, successful theories can describe phenomena that our brains cannot easily visualize. In confronting this, we are challenged to expand our thinking beyond instinct and intuition, and to appreciate that the universe may operate according to principles that are far stranger and more interconnected than we are naturally equipped to imagine.